Talked before, we've all been convinced to leave behind the realm of ordered things and go to fully disordered stuff. So basically that ends my talk. Thank you very much. See you in the coffee break. Yes, exactly. So sorry for that little joke as a beginning. What I'm going to tell you about is how to use embedding methods to do, in our case, simulations on ordered systems. What we're mainly interested here is chemistry on or near surfaces, but these kinds of embedding techniques can be used for much more general things as well. So in the following couple of minutes, I'm first going to try and convince you of why embedding could be an interesting thing to do for whatever you are interested in, and then how we can do that. And I'm going to present a couple of methods. Well, I'm going to present two methods rather roughly on how to do that. Now, as for the why, I brought this graph here, and I'm sorry, this is a bit of an old graph. Probably the scaling is already better, but you all have seen graphs like this, in that the interesting and accurate methods are not necessarily the methods you could afford for bigger systems. So what I did here is I did argon clusters, and I really only went up to argon 16 because I then lost interest, basically. But what I wanted to show here is that as soon as you leave behind your standard semi-local or even hybrid DFT, and keep in mind hybrid DFT does not necessarily scale that well on all codes you might encounter. That is really thanks to the wonderful people here at the Fritz that made this possible, and a couple of other codes do that as well, obviously. But as soon as you go to something more interesting, like double hybrids, like the fantastic RPT2 method, you're in big trouble when you go to systems of realistic sizes. And I think you will all agree with me that argon 8 is not the most interesting of systems to look at. So this is one of the reasons, the cost. But this is not the only reason that you could be interested in this. Now, if you leave behind the realm of metals, and if you do something like chemistry on, for example, semiconductors, you'll soon encounter cases where you see that you have at least locally charged species on your surface, or even local charges doing something, driving the chemistry, for example. So if we're talking of a periodic calculation, if we're simulating anything that is nicely structured, what we do is we use periodic boundary conditions. These periodic boundary conditions in principle mean that while our computer sees that little box on the right-hand side, what we're actually simulating, hopefully, if we do everything correctly, is that. We want to simulate an extended system. Now, what if we do the same thing, but now with a charge in our unit cell? Unfortunately, what you're simulating at the end of the day is this. And as that is an infinite system, basically, with your eval sums and everything, that would mean you would be simulating something with an infinite charge, which you will agree is not very physical. So what the codes in these cases do is they do something called the uniform charge background, which technically just means throwing away the first term in your eval summation, but which physically means that you charge every bit of your unit cell in such a way as to saturate the charge that you put in there, the actual charge. Now, unfortunately, if you do the maths, and I'm not going to bore you with that, you immediately see that this gives you a highly system-dependent energy term now. Because obviously the charge you put in there, and I put a plus charge in here, will interact with your uniform charge background. And the way it interacts depends on how exactly that charge is localized, how big the cell is. Now, if you let your cell go towards infinity, that uniform background will get smeared out more and more, thus reducing this interaction and reducing these energetic contributions which you're losing. Now, that means that what you're doing when you're simulating a charged system like this is that you're introducing a finite size effect that is only there because your box has a finite size. Now, there are methods to counter this, most of which actually mean that you have to do bigger and bigger systems in order to actually see how this finite size effect behaves. Coming back to the first thing, that is probably not something you'd want to do. So what could you do instead? You could do some coarse graining, you could do some embedding. So the example I'll be using throughout is that of semiconductors. The reason for why I'm talking and why I'm insisting on our methods only working for semiconductors or insulators should become rather clear in a second. So the example, and I bring that here because that is really the thing we're looking at the most, is titanium dioxide, which is kind of the fruit fly, or you being physicists, the harmonic oscillator of electrochemistry, in the sense that everybody looks at that first. Unfortunately, turns out it's still not fully understood, or fortunately, because that's what I'm basing my career on partially. Now, let's look at coarse graining. Why can't you just, out of your very big system, take a unit cell, throw that in a vacuum, and see what happens? The reason for that, why you can't and should not really do that, is quite simply, it completely destroys your electronic structure. This now small cluster of titanium dioxide, and I really only represent that by these little dots here in blue and orange, is nowhere near a semiconductor. I plotted the electronic density of states for that thing here. So we took a cluster of a rutile titanium dioxide surface, calculated the DOS. Getting it to converge was a bit of a problem to begin with because it's rather broken, but if you get it to converge, you get something that looks like this. You lose your band gap, so that looks more metallic. The work function is rather off, I'm telling you now. And so why is that? Now, that is obviously because, well, you're lacking the environment. You're lacking all the other atoms that your cluster would see in a periodic extended system. So the next thing to do is you could take something like this. You still don't want to do, for the reasons I told you before, a normal periodic boundary calculations in your DFT. You could, for example, just throw in a couple of charges around your crystal so that it looks like it is or actually in the correct environment. Which charges to take here is one question, also that obviously, speaking of partial charges, only works for roughly ionic systems, so systems that have at least some ionic character. Now, that is the one method I will be talking about, the atomistic embedding method. Another approach, which is even more coarse-grained, would be to observe the following. In order to get the correct, electronic density, the correct electrostatics in your system, you could do something like this, just throw in atoms, and there is a little more detail to that, and I'm going to tell you about that in a second. You could also do something different in the sense that you recognize that what you're actually only interested in is how these charges, how the environment of your cluster responds to the electronic density that your cluster has, the charge distribution, if you will. So that gives rise to a different class of embedding, which I call continuum embedding, which means that you're basically solving an equation or other and simulate the response only on that system. That will still give you a couple of intricacies I'm going to mention later. Now, how that actually looks, I've depicted in these pictures here. So on the left-hand side, you see an actually solid-state embedded titanium dioxide cluster with all sorts of things around. That's why there's blue spheres in there, and there's, I don't know what color that is, these other colored spheres on the outside. I don't know, pink. Let's call it pink things on the outside. And I'm going to mention all that later. The continuum embedding actually comes from a wholly different field, namely that of trying to do away with liquids. So speaking of interactions, reactions on surfaces, what we very often have to deal with is that chemistry does, but rarely, happen in the gas phase. As I said, rarely. Thus, we'll have to add some sort of solvation effects, possibly even electrolytic effects, and the continuum embedding thing, the continuum embedding methods, are a way of dealing with that. The reasons for that are exactly the same. You do not want to have to simulate a very, very big system with lots of degrees of freedom of, for example, water, which do not actually interest you at all. But you're rather interested in the reaction itself. So that's the two methods I'll be talking about. Now let me start with the atomistic embedding. In order for that to work, you'd want to have something that the student, Daniel Berger, who did that, called seamless embedding between your actual quantum region, the region where you do DFT or something beyond, and a classical region where you do simulate the charge carriers classically as, for example, a molecular mechanics force field. Now, technically, we realize that with these three codes, with FHI aims doing the DFT, or, well, the electronic structure, giving you, with the input of the geometry, energies and forces, feeding that into an intermediate layer, which is the chemshell code, which itself does the same thing on the other side, so the side, feeding the geometry to a classical molecular mechanics code called GULP, which gives back energies and forces from the molecular mechanics side. So how does that actually look like? Imagine that we again have our fake crystal here, which has positive and negatively charged sides. The positive ones are the ones in orange, the negative ones in blue. It's orange and blue because that's our corporate identity, and thus not red and blue. Sorry for that. Now, the first thing you want to do is you cut a cluster. This cluster should be rather large for reasons I will tell you in a second. Now, this is not the cluster that you'd want to add in your to have in your QMMM calculation, because that thing is really still a rather large beast, especially if you consider that that is a 2D representation of a 3D object. Now, in this cluster, you, by some sort of criterion, designate QM and MM atoms. The QM atoms being the ones that you'd actually want to calculate with your electronic structure code, the ones that are actually necessary to describe whatever chemistry or physics you're interested in. This being local phenomena, obviously, because something like a phonon you'll probably not describe with something local. Now, the problem is that having a cluster that is ionic like this one, you'll immediately see that your QM region is now neighbored by both positive and negative sites. The negative sites not being a problem, electrons do not want to go there anyway, but the positive sites might be. Because the positive sites are just Q over R, right? That means that you have your Coulomb singularities there. That means that if your basis functions actually reach into that region, the charge will want to go there, because that is a very strong attraction there. This phenomenon has been known for a long time. It's called charge leakage. Simply because the charge that actually you'd want to keep in your electronic structure, in your QM region, will leak out into your MM region. It should not go there because the charges of the MM region are already fitted such as to represent the fully charged, so the new overall neutral system, right? So adding extra charge to that would not be a good idea. So what can you do? The way we chose, and that is really based on the work of many other people, mainly in the biosimulation community where people have done QM, MM for a very, very long time already, is we replace these Coulomb singularities, the positive ones, with pseudopotentials. Now I trust that you know what pseudopotentials are. Basically, it's just a way of faking the existence of actual electrons at that site without having to explicitly calculate them. The pseudopotentials we're using for now are just plain pseudopotentials which you would use in VASP, in other codes, only that the ones we're using right now are norm conserving for various reasons, mostly because we like to have our eigenstates orthogonal. Now, there's still a couple of things missing. We now have a very big cluster that is an MM cluster with a little embedded QM region. We took care of charge leakage, but there are a couple of things that still different from an actual periodic calculation. First and foremost, you will see that, by the way I drew it already, all my little clusters have a quadrupole moment. You will see that along one diagonal there's only the red things on the outside. On the other diagonal there's only the blue things on the outside. I could have drawn it differently such that it has a dipole moment, but in the end you'll probably, simply due to the nature of your cluster having two different kinds of sites and you wanting to have something stoichiometric, you'll probably end up with something that has at least some sort of multiple moment. Also, from your solid state theory, you still do remember that periodic actual extended systems have something called the Madelung potential, which is just the electrostatic potential of an extended collection of charges. Even if that thing is overall neutral, you'll end up with a potential contribution. So there are two things that we still need to take care of. So corrections for the Madelung potential and the multipole moments. In ChemShell, and we did not come up with that, that was already in there, this is fixed by fitting charges to the potential of an actual periodic calculation, which are made blue here for a reason. But yeah, so the fitted charges are then put on the outside such that in the QM region, the potential of an actual periodic calculation is restored. That is quite important if you're doing things like, for example, electrochemistry. If you're doing anything where the actual position of the work function of your material is important, because the Madelung potential is what fixes the position, well, among other things, what fixes the position of this work function. By changing this potential, you could just shift your work function up and down rather easily. Now, having a wrong work function could very much influence the kind of reaction that you're getting. So I brought an example on what you can do with that from the work of Daniel Berger. It's been a couple of years past already that he did that, but the example that I'm bringing here is that we looked at a defect, which is, as we heard, where things start to rust. So we actually do have defects in our simulations. A defect on a titanium dioxide rutile 110 surface. Now, the importance of these defects will become clear in a second. Safe to say that they heavily influence the kind of chemistry that you will get on that surface. So what we were looking at were a couple of different defects, and I'm sorry that, yeah, you can probably read that. So these defects are all oxygen vacancies. So basically we just removed one oxygen from the top layer of our titanium 110. But this being a crystal with ionic character, that gives rise to a couple of differently charged defects now. If I take away the oxygen, which in the extended system is negatively charged, it grabs a couple of electrons from the titanium, you can either leave these electrons behind, leaving a neutral defect. You can take these electrons out, or you can take one of them out. That means that that gives rise to 3 differently charged defects, and there is a 4th one here, which is just us looking at if the neutral one is a singlet or a triplet state. So we have a doubly charged defect, a neutral defect, and a singly charged defect. For these, we calculated the formation energy, which is shown here on top. So basically, the energy it costs, or the system gains in that case, to form that defect. This being a graph means that we don't actually know the doping state of our system. So by doping, you can shift the Fermi level. You can make the system to be more in one state than another. What you can see, though, is that for all the conditions we're looking at here, the doubly charged one, the one I now painted in red, is the most stable one. It is energetically below all the other defects. What that means is that this oxygen vacancy traps 2 positively charged carriers, so 2 holes near its position. These 2 holes, well, that is basically what the spin density looks like for this kind of configuration on the right-hand side. Now, why is that important? For things like electrochemistry, which are driven by charge carriers, electrons and holes, having holes already localized somewhere on the surface is actually a big thing. Because a localized hole is in the end what will drive the reaction. Now there is one more thing I did not mention before, only in passing. In assigning our MM region, I told you that we use a force field for that. We put MM charges there. That is not quite all. And this is not quite all because what you need, as I said before, in order to have seamless embedding, is you need to have the response of the environment on your QM region. That response of the environment on your QM region means that the force field you're using needs to have at least some degree of polarizability. Because in the end, what you want to get is you want to get the dielectric permittivity of your medium right. Turns out for titanium dioxide, that is rather unfortunately complicated because it is highly anisotropic and it is rather high. Along one of the directions, the relative permittivity is 200. So getting that right would be rather important. So in order to show you how important that is, I actually have a graph here, again, prepared by my former student Daniel, of how the ionization potential of our cluster, which is related to the work function of the periodic material, changes if we change the dielectric permittivity. So on the very left-hand side of that graph, we have a completely non-polarizable model. And on the right-hand side, we're getting closer to what at least the high frequency, the electronic permittivity of the system should be. And you can see that, I plotted in blue here, where the IPs or the work function should actually lie. And you can see that without polarizability, you're nowhere near the correct result. This, in turn, so now you could say, okay, that's just where my levels lie. That's probably unimportant if you're only looking at relative things. Unfortunately, that is also not true. If, for example, we look at the binding energy of an OH group, and the reason why it's an OH group is because that is one of the intermediates in a water oxidation reaction, which, if titanium dioxide is the harmonic oscillator of the electrochemistry world, this is the reaction of that harmonic oscillator. This is the reaction everybody likes to understand here. Now, the binding energy of an intermediate obviously will influence how a reaction occurs or not, if the binding energy is too far off. So getting this right is a rather important bit as well. Now what Daniel showed here is actually two things. First of all, again, by getting towards the right dielectric permittivity of the surrounding medium, you do get some binding energy that is closer to what you would get in a periodic boundary calculation. The second thing that he showed is that actually the clusters which we're using, and there's two clusters here right now, it's titanium 17 oxygen 34 and titanium 33 oxygen 66, have less of an impact on the binding energy in this very case. That is just one example. There's obviously other examples which I can show you where the cluster size has more of an impact, but the importance is that although there is an impact, I mean it changes by 100 millieV, it is much more important to get the embedding right than having that cluster big. Now you might ask that, all right, but what happens if I take a really, really big cluster? Should you not recover the binding energies that you would get in the periodic boundary calculations? And the answer to that is yes. If you go to some absurdly big clusters, obviously the whole chemistry should again converge. So you also remember that in the beginning I showed you a wrong density of states for titanium dioxide. What you would get if you just take your titanium, I think it was even 17 oxygen 34 cluster, and don't do anything clever with it. Now, just to show you that we are actually doing something clever with it, is I show you now how the embedded cluster looks in comparison to the periodic boundary calculations. Now, the slab calculations are now in blue, and in red we have the embedded cluster. It is one of the slightly bigger ones, but that is just to show that all the states below the band edges do converge towards the right behavior as well. And you see that not only do we get a band gap that is very, very much in agreement with the periodic calculation. We also get a work function, meaning we also get an alignment of the whole thing that is very, very good compared to the periodic boundary calculation. And now I'm going to change gears completely. I told you the second thing I'd like to talk about, and I still have some time left, I'm sure, is the continuum embedding. That is why I ended here on the note of having the right dielectric properties, because that is now what we'll be talking about in the next couple of minutes. Now, the example I'm using here is a molecule, and that is simply because our periodic code is still under development. So I cannot show you any surface reactions with that yet, but I'm going to show you what's happening on a molecule. Now, you've heard about DFT. You know about electrostatics. That means the equation, although written rather weirdly here, should not be new to you. This is simply the Poisson equation for a given density, which I call N solute, N sol, which gives you a certain electrostatic potential, which I call V. I left out an epsilon so far, but and a couple of constants, but as you know, constants are not that important after all. If we're doing a calculation of this molecule in vacuum, this is the equation we solve. There is no additional epsilon relative permittivity that influences anything. But then again, that is not necessarily what we're interested in. If we put this solute, this molecule, and please do not ask me what kind of molecule that is, I forgot. I've been told, but I forgot. I'm also not a chemist. If we put this molecule into our solvent, whatever that may be, what we're effectively doing is we throw that into a continuum in this model, into a continuum with a certain dielectric permittivity that is different from 1. Meaning that we now represent our surroundings not as point charges wiggling around, but rather as a continuum that itself can be polarized. So we took that from macroscopic electrostatics, where you really do solve these kinds of equations. Now, this added another term to our Poisson equation, which is why we call that the generalized Poisson equation. The other term we now get is an epsilon of n electrons. Why is that a function of anything? Why don't we just have an epsilon that is different from 1, possibly 80 if we're throwing our stuff into water, and leave it at that? The reason being that if you want to simulate something like solvation, your solvent molecules will most likely not penetrate your solute. Meaning the continuum that provides your dielectric response will not penetrate the solute and will not penetrate a certain area, a certain region around that solute to begin with. That is rather easy to see that, well, you have this molecule here. Water will come close to that molecule, but will certainly not penetrate it, because there's other atoms in the way. That means that epsilon is now spatially dependent, meaning that close to your solute, you still want to have something that has a permittivity of 1, as you would have in vacuum, because there is nothing that could provide a dielectric response there. There's just your electronic density and your nuclei, but these are already taken care of by your DFT or whatever electronic structure method you're using. The way we parameterize our epsilon is a rather simple one. Instead of saying that, yes, we figure out a function that somehow attributes regions of space around the molecule to the region that has permittivity 1 and other regions to something that has permittivity, let's say, 80. We simply use the electronic density because that is already such a partitioning. So we could, for example, say that from a given electronic density iso value, so everything having a higher value than that, meaning having more electrons than that, is close to the molecule and thus will have 1. Everything that has a lower iso value is far away from the molecule and that will have this whatever permittivity you're interested in. Now, in this model, we're actually doing something slightly more clever. We recognize that there is no hard boundary which your water molecules can't penetrate, but there is probably going to be some sort of smooth function going from 1 to 80 or whatever the bulk epsilon is supposed to be. So we're actually using a function that has two parameters. One, where this smooth transition from one value to the other starts, in min, and another parameter that tells us where that ends. So that's the first two parameters which determine the shape of this solvation cavity where my solute resides in. The other three parameters, alpha, beta, and gamma, I wrote here, are actually parameters for the non-electrostatics. Because if we're talking about something like solvation, only looking at the electrostatics, unfortunately, will not cut the mustard. What in solvation you will get beyond the electrostatics, and this is an important and dominating factor very often, are things like dispersion, so van der Waals forces. There is a cost associated with generating the cavity your solute resides in. There is something like surface tension. These are things that need to be taken care of. And while I do not want to bore you with the exact details of the non-electrostatic model we're using, there are a couple of parameters associated with that as well. Now, in the introduction, I also mentioned that what you could also be interested in if you're looking for chemistry happening in your solvent, you might be interested in the effect of electrolytics. So you might be interested in the effect of ions dissolved in your solution, because very often these can make or break a reaction, it turns out. This can also be taken care of. We just need to add one more term to our generalized Poisson equation. Namely, we add a ionic charge density, which is called NPB ion here. The reason why it's called NPB is because the model is now a Poisson-Boltzmann equation, because for the ions, we simply assume an equilibrium distribution according to the Boltzmann distribution. Unfortunately, that again adds a couple more parameters. First of all, the method we're using is actually an ion, a size modified Poisson-Boltzmann equation, meaning that our ions are not point charges. They obviously are not. They are simply because the ion itself already has an extent, and in solutions such as water, you'll have a solvation shell around the ions as well. Also, the ions cannot penetrate your molecule, blah, 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 and this layer that forms here is called the Stern layer, and that does not necessarily have the same shape as our solvation cavity. So if we put all of that together, that is in principle what it looks like. Unfortunately, we end up with 8 parameters which we have to fix somehow. I don't know why I added that picture. Sorry. So now, you might add, okay, you have a model with 8 parameters. We all know the rather famous quote by John von Neumann, which was retold by Enrico Fermi, which is that, well, with 4 parameters, I can fit an elephant, and with 5, I can make it wiggle its trunk. Now this, luckily, has recently been proven to be actually true. You can look it up in this publication here. People in the American Journal of Physics showed that with a 4-parameter function you can fit an elephant function, and with the 5th you can make it wiggle its trunk. What that means is that having a model that contains too many parameters which you do not have a physically reasonable way of determining makes the model slightly questionable. Because by just with enough parameters, you can fit anything. So how do we fix our parameters? First of all, we need to fix our solvation parameters, which we're for now going to fix separately from the ionic parameters. We do that by having a, well, large test set of experimental solvation free energies and fit these to that. This is the database which we have. This is the actual deviation of our solvation free energies from the ones given by experiment, and they're on the order of, well, up to a couple of 100 millieV, this being an effective model that is probably not very surprising. What is interesting is, if you want to know how good we are with respect to other people, I also plotted here a different model by Mazzari and co-workers, and that gives basically the same results. But how do we fix the ionic parameters? And I'll probably skip this in the interest of time. Our latest approach to fitting the ionic parameters is via the so-called Sechenov coefficients. The Sechenov coefficient is just based on the observation that if you throw a neutral molecule in a solution and then add salt to the solution, the solvation free energy of that neutral molecule goes more or less linearly with the salt concentration. It holds for low enough salt concentrations, otherwise stuff gets weird, and generally these Sechenov coefficients are positive. The effect that gives is called salting out, meaning you throw in salt, your neutral solute will fall out and just form a layer of stuff at the bottom of your beaker. So what we did there is we used these experimental Sechenov coefficients and we split stuff up into a training and a validation set to fix our parameters, so the 4 parameters that we were still missing for the ionic part of our model. And you see that, well, mostly we're not too far away. We're, again, in the range between 100 to 200 millieV for the Sechenov coefficient, which is now not just solvation free energy, but which is the slope of a solvation free energies. I now could bore you with how we actually solved that equation, because the equation, unfortunately, is a highly nonlinear beast. Solving it is not entirely trivial, and it took Stefan Ringe, the student who did it, his whole PhD to basically get that done. But he came up with the help of Sebastian Matera and others, came up with a very nice method, which is based on a multipole moment expansion relaxation method called MERM. But I'll skip that for now. So let me end by thanking all the people who did the work. So Daniel Berger working on the solid state embedding, Markus Sinstein and Stefan Ringe working on the implicit solvation stuff. And you for your attention. Thank you very much.